Now let us see existence and uniqueness of solutions using Lipchitz condition. Okay, so before that we will see a recap of what we had seen in the last session. So in the last session we had seen that given any ODE which is linear or non-linear with an initial condition, there exists a solution for the system if the function f is continuous, and if dou f by dou x is continuous, then the solution would be unique. Okay, so we also had stated the existence theorem and the uniqueness theorem along with some problems also. Okay, so now we will see what is the Lipchitz condition. Okay, so Lipchitz condition states that we can define a constant L which is greater than 0, a bounded value, that means there exists that means a function f defined on the equation that we had seen above. It satisfies the Lipchitz condition on any domain D if there exists a constant L, that means L is bounded. There exists means L is bounded. Okay, L is bounded and is greater than or equal to 0 such that this condition is satisfied. So what is this condition? So I will draw it here. This is f of x1, let this be x1 and x2, f of x1 and x2. So if I take the function, some function here, some function between lying between x1 and x2. So what is this inequality? F of t comma x1 minus f of t comma x2 by x1 minus x2 is effectively the slope here. So here I have taken the dependent variable here, which in fact depends upon time also, and here I have taken f as a function of t comma x here. So this point would be something like x1 f of t comma x1, and this point would be sum of f of t comma x2, f of t comma x2. So the function it satisfies the Lipchitz condition, showing that if the slope is bounded, okay, so if I try to draw the slope here, if this would be some slope here at this point, this would be the slope here, and it shows it is bounded. So this when will it not be bounded? As this goes and becomes vertical, what happens? The slope will not be, this function L will not be bounded. So we will see an example for that. So for example, this is a continuous system, and so this L is bounded here. So I can get some L with some constant value which is greater than or equal to 0. Okay, so we will see a system which for which this L goes to infinity. So this is the same problem that we had seen, a discontinuous function here. This is 2, this is for example, and this is 2 and this is 4. For example, this is some 2 here. What happens here? If I try to take x1 and x2 here, at these 2 points, if I choose x1 and x2, I can get a slope which is bounded. Okay, but now if I try to reduce the domain here, if I have the initial points somewhere here, and if I try to take points closer and closer, what happens? This L, if I try to take here this and this points, what happens? This L goes on increasing, the slope goes on increasing, that L goes on increasing. So when will it be infinity? So what happens? This becomes when it becomes vertical, what happens to this value? This tends to 0, and this divided by this, that means f of t comma x1 minus f of t comma x2 norm of this divided by the distance. If the distance is reduced to 0, what happens? x1 minus x2 is reduced to 0. What happens? This goes to L, goes to infinity. So it will be unbounded, showing a discontinuity in the system. So but whereas for continuous systems, what happens? This kind of a condition will not occur. L will always be a constant with a bounded value. So that is called a Lipchitz condition. So this has applications on the continuity of the functions, which later have applications on the existence of solutions as well as uniqueness of solutions. Okay, so that is why this Lipchitz condition is very much important here. Okay, so now we will see some examples on how to find out the Lipchitz constant here. So here I will try to find out f of t comma x1 minus f of t comma x2 is equal to t squared minus 2x1 minus t squared plus 2x1 minus t squared minus 2x2, which can be written as 2 into x1 minus x2. So I can finally write this as less than or equal to some 2 into x1 minus x2, for which I got a constant 2 as a Lipchitz constant here. So what can I say about this function? This function satisfies Lipchitz condition. Okay, now we will not speak about the existence of the solution. We will see to that later on. Okay, so what about this? So f of t comma x1 minus f of t comma x2 is equal to norm of x1 minus norm of x2. This is the function here, f of this is less than x1 minus x2, right? This will all definitely be less than this, giving us this function satisfying the Lipchitz condition here. This definitely is less than this because I have taken here the mode of this minus mode of this will definitely be less than this. Okay, so what happens here? This mode of x is Lipchitz condition, Lipchitz continuous. Okay, so f satisfies Lipchitz continuity. What about root x? So this you can try out. What about root x? Whether it is Lipchitz continuous or not, I will give another other problems also, but this you can check out. Okay, so now we will state the local existence and the uniqueness theorem. So here if you look at this these lines here, we can see that the Lipchitz constant gives us more intuition into how the solution, how the curve lies here. So it shows the continuity of the function here. Okay, so definitely the existence of the system is guaranteed. Okay, so now we will go and look at the theorem and see that Lipchitz condition is, if the Lipchitz condition is satisfied on f, then the uniqueness is also guaranteed for the system. Okay, so without proof we will state the theorem here. If f of t comma x is piecewise continuous in t, and if it satisfies the Lipchitz condition on for all x comma y element of B in some domain B, and this here we have taken x as an element of Rn, and x minus x0 is within a particular region, within a ball R. This is because the only here it is taken within a particular radius. Okay, this is because we are going to speak only about the local existence of functions. We are only speaking about the local existence of functions, and if this Lipchitz condition is satisfied, we can say that the function f has a unique solution. Not the function, the equation 1 has a unique solution. Okay, so this is about this is a theorem on local existence and uniqueness of theorems. This only shows that within the neighborhood of the initial condition, or within the neighborhood of the initial, that means x0 t0 initial condition, t0 comma x0, we have the existence or uniqueness is guaranteed, but it is not true for the whole domain. Okay, so that is why it is called as a local existence theorem, because we had considered only a small ball here. Now, if this condition is true, if this Lipchitz condition is satisfied throughout the whole domain of the system, then we can say that we have a unique solution throughout the whole domain of the whole domain of the system, given system. Okay, for the given system. Okay, now this is about the local existence and uniqueness theorem using the Lipchitz condition. And there is a lemma which shows that this lemma shows that when does f satisfy this Lipchitz condition. Okay, so here we saw that if the Lipchitz condition is satisfied and if the function is piecewise continuous, then we have a unique solution. Okay, that is what we saw in this theorem. So now what we have to see is this lemma. So when does this satisfy? When does f satisfy the Lipchitz condition? So that is given by this lemma. Okay, this can be satisfied when if dou f by dou x exists. Okay, this goes back to the previous lecture also. That means if dou f by dou x exists, it means the partial derivative of f with respect to x exists, and if it is continuous, then what can we say that if it is continuous, and if we can find out some k greater than 0 such that dou f by dou x is less than or equal to k, then the Lipchitz condition holds with L equal to k. So we will see the proof of that. So what does this condition say? Now we will try to find out the conditions here. We will see f of t comma x minus f of t comma y. What is this? Is equal to, I can write this as integral of x to y, right? Dou f by dou x t comma x, right? Dx. So this is that. Okay. So now what is it? Dou f by dou x. Now I will try to take the norm of this. So I will write this as f of t comma x minus f of t comma y is equal to integral x to y magnitude of dou f by dou x t comma x dx, right? T comma x. So what is this? If this is less than k, then this is satisfied. That is what it is said by this lemma. Okay. So now if I take this less than or equal to k, I can write this as less than or equal to integral x1 to x2 of k dx, right? So I can write this as less than or equal to, k is greater than or equal to 0. So I can write here as k integral x1 to x2 of dx. So in fact this is also there actually. I forgot to take this here. This is here, it will be dx here, then it will be correct. So I have this here, so this becomes less than or equal to k into x1 minus x2. So what does this say? If this the partial derivative of f with respect to x is less than or equal to k, then what happens? This is satisfied. That means by default the Lipchitz condition is satisfied. So when does a function f satisfy the Lipchitz condition? If the derivative of f with respect to x is continuous and it is bounded by some constant k, then this Lipchitz condition holds. Okay, with L equal to k. So here L will be equal to, L becomes equal to k. So this becomes equal to k. So this is the lemma which states that. So that is why from this theorem what it says that if the Lipchitz condition is satisfied, the system has a unique solution. It is from this equation actually whatever we had, if dou f by dou x is continuous, then the system has a unique solution. So everything is interrelated. Okay. So now we will see some problems and see whether this is the solution exists for this system using the Lipchitz condition. Okay. So now we first what we will see, whether we will check for whether we'll see what is the Lipchitz constant for this. So here we have f of t comma x1 minus f of t comma x2 is equal to this t and t gets cancelled, that is magnitude of tan inverse of x minus tan inverse of y. Okay, this definitely is less than or equal to some L, sorry, this is x1 and x2, because in the previous thing I had written as y, so the condition is there, x1 x2. So into this definitely is less than x1 and x2. Okay, tan inverse of x1 minus tan inverse of x2 will be less than some constant L into x1 minus x2. So this says that the Lipchitz condition is satisfied for this system. Satisfied. Okay, satisfied. Now we will also see whether dou f by dou y is bounded. Since the Lipchitz condition is satisfied, we will also see dou f by dou x. What is dou f by dou x? Dou f by dou x is equal to 1 by 1 plus x squared, right? The derivative of tan inverse of x is 1 by 1 plus x squared. So what is the magnitude of this? So this implies dou f by dou x is equal to magnitude of 1 by 1 plus x squared. Right. So this for all values of x, what happens for all values of x, this value is bounded. Okay. So this will be less than or is equal to some k. So now this can be from this also I can say that since this is the derivative exists here and is bounded by some k, the Lipchitz condition also holds here. Okay. So now we will go and look into this example here, which is an interesting example here. So this is a function something like this. Something like this. Something like this. Okay, this goes. Okay. Okay, it's just 1 by 3, something like this. Okay, so this shows that this function is not defined at x is equal to, this function is continuous function, but the derivative does not exist at x is equal to 1 by 3. So what is the derivative of dou f by dou x? What is the derivative of it? Dou f by dou x is equal to 1 by 3 x raised to minus 2 by 3. Okay, so if you look at the derivative of this, we can say that it does not exist at x is equal to 0. So this does not exist at x is equal to 0. So that this means that it is not locally Lipchitz at x is equal to 0. Therefore, this function x raised to 1 by 3 is not locally Lipchitz at x is equal to x raised to x is equal to 0. Okay, right. So now what can we say, that if this function is also not differentiable at x is equal to 0. Okay. So now this equation, we cannot say whether a unique solution exists for this or not. Okay, so now we will see another example here. This is mod x. Okay, and then we will come to a conclusion of this. So mod x, we saw that it is what is it? We have f of t comma x1 minus f of t comma x2 is equal to magnitude of mod of x1 minus mod of x2, which definitely is less than some constant into x1 minus x2, which is equal to 1. Here this is definitely is less than this. So if I take this mod of this, okay, absolute value of this is less than this. So this definitely is less than this, showing that L is bounded, and therefore this function mod x is locally Lipchitz, or locally, in fact it is it has a Lipchitz constant here, and the Lipchitz condition is satisfied for this function. So you can verify this also. Maybe if you didn't understand that why this is not why this is less than or equal to L of absolute value of x1 minus x2, you can plug in some values and check whether this is correct or not. Okay, so now the important point that I wanted to stress here, this in the last session what we had seen here is this is mod x. So we saw here that this function is not differentiable at x is equal to 0. At x is equal to 0, it is not differentiable. It is not differentiable. This we had seen in the last class. But what does it say? This function is Lipchitz continuous everywhere in the domain. So even if it is not differentiable, we can say that it is a Lipchitz condition is satisfied. So differentiable, if a function is differentiable, so the statement is very important. If a function is differentiable, this implies Lipchitz, the function is locally Lipchitz. From which theorem? From the theorem which is here given here. If a function is differentiable, then the function is locally Lipchitz. Okay. And if a function is locally Lipchitz, definitely the function will be continuous. Definitely will be continuous, because Lipchitz is a stronger notion for continuity. Okay, so showing more closeness of the values with respect to x1 and x2. Okay, so if the function is locally Lipchitz, it definitely means that continuous. But if a function is continuous, it does not mean that the function is the function is locally Lipchitz. Similarly, if a function is locally Lipchitz, it does not mean that the function is differentiable. Okay, so these are the certain things of interest, and what you have to understand here is you have to see that a solution exists for a given equation if f is continuous, and a stronger notion for, and if it is continuous as well as if it has a Lipchitz continuity, then the solution the solution would be unique. This is what is said in the first statement itself. For here we had stated continuity as well as Lipchitz continuity. Lipchitz continuity is related to dou f by dou x. So that means if dou f by dou x is bounded, and if it exists and if it is continuous, then the Lipchitz condition holds here. So this is about Lipchitz continuity and existence and uniqueness of solution. So with this we come to an end of the second module. So we will do some problems based on the second module. Okay, thank you.